We are the team Aerospace Peru of the Smart Machines Laboratory of the Technology of the National University of Engineering in Lima, Peru, and in this Latin America Space Challenge, we come with the Kuntur project in the category of solid propellant rockets of 1 kilometer, from the Andes to the stars. Our team focuses on the study of the technical pillar for the development of manned and unmanned spacecraft. In the mechanical part, we detail the aerodynamic study and design and selection of composite materials. In the avionics, it details the embedded system for sensor measurement, ejection and recovery system, telemetry and payload. In the propulsion part, the calculation of the appropriate rocket motor for the mission is detailed, and in the interface part, the data is sent to a ground monitoring device. The present slide details the parts and segments of the rocket with the propulsion system with three fins in the intermediate length diameter at the end. The rocket has variable diameter to reduce weight. The rocket has four materials that integrate all its construction: carbon fiber in 80% of its entire structure in the fins and cylinders, fiberglass for the telemetry section and board command ogive, aluminum as a skeleton in the rings and bottom for the location of the engine, and 3D printing for the encapsulation of the payload and the installation of the motor. The system in general is detailed below, showing the inner part of a Pro 54, the commercial electronic system to measure the experiences of fin deformation and kinematic viscosity in flight by pressure difference tube, and the expulsion of the payload for the sensing and interaction of the biological load consisting of bacteria from the Peruvian Andes capable of generating changes of state in the water. We can see on the right side the composition of the payload kinting, its electronic system, the geometry, and recovery system. This experience and future approach can be applied to counter the floods that generate heavy and economical losses at the civil and industrial level in the north of Peru. For this reason, we won the Innovation Prize in Peru in 2018, awarded by the Society of Mining, Petroleum, and Energy of Peru. The geometrical dimensions of the rocket are then established from the weight of the rocket alone, the center of mass from the base, the total length, and the reference diameter, which is usually the largest. As previous diameters have been chosen, there are reductions that must be considered for lift effect. Finally, three fins are considered with dimensions shown in the table below. According to established calculations, where the flight lift coefficient is compared in a stability diagram, according to the diameter reference, the following parameters observed in the table with respect to lift, torque, and fitness have been established. These are the geometrical measures for a solid fuel engine Pro 54 of sorbitol composition. The following specifies the physical and energy values provided by this engine, such as total weight, gravity input, maximum thrust, burn duration, total impulse, etc. At the same time, the trench thrust curve and point parameters for trajectory simulation. Before that, to observe the trajectory of the system, including kinematics, it is necessary to know the dimensions of the parachute, which are shown and exert the resistance at higher velocities. After that, the surface area of the parachute is considered in addition to the characteristic of the launching system, a launching length of 4 meters, a specific angle. In addition, to establish the trajectory, it is necessary to take into account the starting mass, the wind speed, which is 5 meters per second orthogonal to the flight duration. The calculations are run and you have this trajectory. It is compared with the Eiffel Tower on the detailed X, Y, and Z curve. After that, the comparative of the launch and landing are established in a kinematic way, establishing maximum values in a velocity, acceleration, and height, as shown in the following table figures. The force versus time curve is shown below, comparing thrust, weight, and drag force. Acceleration versus time curve, longitudinal acceleration, and other descent panorama are shown below. The speed versus time curve is shown below. The position versus time curve at range and altitude. And finally, we can conclude that the proposed flight according to the design variable diameter of the rocket is stable. The other conclusions are shown. Thank you very much for your attention.